Okay, this is probably our last video on slope fields, but I wanted to do a little bit of matching, largely because it helps us to think through why the slope fields have the shape that they have and what they're really trying to communicate to us. Okay, this is page 2 of that worksheet by Nancy Stevenson that I was telling you about, and this is basically a good matching exercise here. I have 4 slope fields and then 4 differential equations down here, and we need to determine what's going on here. Let me go ahead and see if I can. I'll just push the camera down to zoom in a little bit. Okay, and I think that gives us a better view. Now, let's go ahead and look at this first one. How about let's look at A. Okay, now I notice that what happens is I have what looks like a horizontal asymptote right up here, okay? So I know that the slope is going to be 0 at y equals something, okay? I know that below that asymptote, it looks like all the slopes are positive. And I know above that asymptote, it looks like all the slopes are negative, okay? And I know that basically it's wholly dependent upon y because it's the same all the way across, okay? At this y value, it's the same for every x. So x does not actually enter into determining the slope right here at this y value. It doesn't factor in at this y value either. All the way across at whatever y value this is, it's consistent in terms of the x not contributing to the slope at all. So I'm looking for something that is going to give me a horizontal asymptote at y equals something. It's going to have no x values at all in the differential equation. And I'm looking for something that's going to generate positive slopes beneath that asymptote and negative slopes above it. Well, there's really only one that excludes an x value, and that's this one right here, okay? That could be y is equal to 2 right here. And so if y is equal to 2, I know that the slopes are going to be 0. Now, when y is less than 2, let's say when y is equal to 1 or 0 or even negative 1, I'm going to get a positive difference. So that actually does indeed make sense out of the positive slopes that are underneath that asymptote. But when y is greater than 2, I'm going to get a negative, okay? I'm going to get a negative slope. So this right here is number 9. Okay, well that handles that one. Now, let's look at B. I have, in some sense, kind of the opposite thing going on here in B as I had in A. I notice that along any x value, the y is not contributing at all to the slope, okay? So I'm looking for one that has no y in it. Okay, well that basically narrows it down to these two from the remaining ones, right? Now, I know that sine is the derivative of negative cosine. And I know that if dy dx is equal to sine, then this is going to oscillate. This does not oscillate, okay? This actually is number 10 right here. Number 10 is B. And if you actually look at it, you can actually see, because, I mean, this one is going to be from 1/2. This is from y is equal to 1/2 x squared plus c, right? That is how we got down to dy dx is equal to x. You can actually see, you can see the parabolic nature of the solutions depending on what your initial condition is. Okay, well that sort of gets that one out of the way. Now let's go ahead and look at this one. This is obviously going to be the sine one. This is too erratic, and you see the oscillating nature of it if you actually look closely. And we see the fact that up and down and up and down. And that's that's pretty much what's going to happen here for this particular one. Now, the oscillation makes this number 7. Now, obviously, by process of elimination, number 8 is D, but I want to reason through it before we move on to the next set of matching. dy dx is equal to x minus y. Now remember what I did for the last one that we did this for, okay? I transformed it into y is equal to x minus y prime, okay? Now this is a linear with y prime, or negative y prime, being the y-intercept. So when y prime is equal to 0, it's going to happen on the y is equal to x line. Notice that on the y is equal to x line, right here, all the slopes are 0. Okay, well how about what happens with the slope at, I don't know, let's do the slope at 1. If the slope is 1, I know that it's going to be at y is equal to x minus 1. Y is equal to x minus 1 is this line right here, and all the slopes along y is equal to x minus 1 are indeed a slope of 1. And at y is equal to x plus 1, all the slopes are negative 1, okay? And so we can sort of reason through based upon x and y values and how they relate to each other. And this, of course, is the only one out of the 4 that actually is dependent upon both x and y. And we can see the difference, okay? This one right here, just like B, there was, on any given x value, there was no variation in the slope as you go up and down along that x value. Y does not factor in. But notice as you go up and down along any x value, it does change. And then go along any y value, the slope does change. Which means if you go up and down along any x value and the slopes change, and then go along any y value and the slopes change, you know that the differential equation has to involve both x and y. It's not dependent upon one variable, it's dependent upon both, okay? Let's go ahead and move on to the next one, okay? Now notice, A, we have, again, and this is a good example of what I was just talking about. Let's go along y is equal to 0. Along y is equal to 0, they change. Go along x is equal to 1, or what looks like the first hash mark, and they change. So this is basically dependent upon both x and y. That rules out number 11. That rules out number 12. It's probably not this one because we already know what this one looks like. I've actually shown it to you twice now. This one is D. Okay, so the only one that it can be is number 14, but let's go ahead and confirm it by reasoning it out. I recognize the fact that this can be written as y prime is equal to x plus y, or y is equal to negative x plus y prime. Now, if I look at y is equal to negative x, if I look along y is equal to negative x, do I get a slope of 0? Yes. If I look along y is equal to negative x minus 1, do I get a slope of negative 1? Yes. If I look along y is equal to negative x minus 2, do I get a slope of negative 2? Yes. If I look along y is equal to negative x plus 1, do I get a plus 1 slope? And the answer is yes. This is number 14. Now, let's go ahead and look at both of these. Both of them are dependent upon a single variable. So you could make the decision based on the two that are left, just based on that fact alone. This one is based upon x values. Okay, so up and down on any x value, it's constant. So basically, you know that the slope is dependent on where it is along x. Here, it's one slope. Here, it's another slope. Here, it's another slope. So it's dependent upon x. That means it's number 11. Okay, and same thing here. This is number 12. It is wholly dependent upon y, okay, and it almost looks exponential. Because it is, okay? If I were to separate the variables, it actually separates like that. I'm going to, when I integrate, get a natural log y, and then in order to get rid of that natural log, I'm going to have to exponentialize both sides, thereby giving us this either positive exponential or negative exponential, depending on what the coefficient is in front of the e to the x. Okay. Now, that is matching based upon the differential equation and the slope field. Let's do a little bit of matching based upon not the differential equation, but how about a solution to the differential equation? Okay. Now, and they're down at the bottom here, but let's go ahead and walk through this a little bit. D, that ought to be pretty easy. The slope everywhere is 0. What gives you a slope of 0 everywhere? Well, a constant function gives you a slope of 0. Where's the constant function? It's right there, okay? So D is number 7, okay? That was easy enough. Now, let's go ahead and let's look at this one, okay? And let's go ahead and zoom out just a smidge so I can actually include the functions at the bottom. Which one of those looks like it actually fits with that? I'm thinking that number 11 is going to be the best fit, okay? Number 11 is going to be the best fit because you notice that if you were to actually take the derivative of number 11, okay, if you have y is equal to x to the negative 2, you have dy dx is equal to negative 2x to the negative 3, or negative 2x cubed, okay? So the derivative is negative 2x cubed. Does this look like dy dx is equal to negative 2x cubed? Okay, well, where x is positive, do I have negative slopes? Yes. Where x is negative, do I have positive slopes? Yes. As I get closer to 0, do the slopes get steeper? Yes. As I get farther away from 0, x is equal to 0, do the slopes get flatter? The answer is yes, okay? This right here is number 11, okay? Let's look at here number 8. Now this ought to be almost as easy as number 7. Number 8 gives me y is equal to x, okay? That is basically from dy dx is equal to 1. Okay, dy dx is equal to 1. The derivative of this is dy dx is equal to 1, meaning the slope everywhere is 1. What does that look like? This looks like the slope everywhere is equal to 1, okay? And it looks just as simple as this one. Okay, now let's go ahead and look at y is equal to x cubed. Y is equal to x cubed. Okay. Now, y is equal to x squared. Obviously, this, if you take the derivative, is going to be what? Well, it's going to be dy dx is equal to 2x, okay? So what we're going to get there is we're going to get derivatives at x is equal to 0 equal to 0, okay? If you know that this gives you y prime is equal to 2x, is it this one? No, because the slopes here are positive everywhere. Is this going to give me positive slopes everywhere? No, okay? This is going to give me positive slopes where x is positive and negative slopes where x is negative. Okay, well that looks like a pretty good one. Is that what's going to happen? And that's going to be no as well. Now that's correct on the fact that it's got positive slopes where x is positive and negative slopes where x is negative. But notice, as this slope field designates, or shows, it demonstrates that the solutions, as they get closer, get steeper, okay? Which is not the case for a quadratic, right? As it gets closer to 0, it flattens out because that's where its vertex is going to be, and it's going to have a change of direction. It's going to turn around and go the opposite way. This one is not going to help us because this one oscillates, okay? So what we have here is this is the like C right here is the only one that really helps, okay? C, this is number 9. Okay, well, let's go ahead and leave cosine and sine for the end, okay? Which one is this one going to be? Now, we obviously know what natural log x looks like. And natural log absolute value of x opens up the possibility for negative inputs, okay? That is going to be a positive slope where x is positive. That's going to be a negative slope where x is negative, and it's definitely going to be steeper as it gets towards 0 because it has an asymptote at x is equal to 0. This is number 14, okay? And think about it. This is what we're used to seeing in terms of the behavior of y is equal to natural log x, right? And this right here is y is equal to x squared plus c. And this right here, so you can actually draw the solutions in here to give yourself a better idea of what you're doing. Now, obviously, by process of elimination, we have e and b both as oscillating functions. F is obviously going to be number 10, okay? And that happens because we see the fact that it's just going to come up, lay flat, and then go back up again, okay? That is basically just as a vertical shrink on the parent function of cubics. And of course, we see the fact that it's positive everywhere because this gives me y prime is equal to 1/2 x squared. This is, and 1/2 x squared is positive everywhere except for x is equal to 0. So it's non-negative everywhere, which indeed accords with that slope field. The only thing left to do is figure out which one of these is cosine and which one of these is sine. Okay? And it's really, really easy. All you have to do is remind yourself, when is sine equal to 0? Because this comes from dy dx is equal to cosine x, and this comes from dy dx is equal to negative sine x. Doesn't it? So, if we know that dy dx is equal to negative sine x for negative 13, I know that I'm going to need a slope of 0 where? Well, doesn't this look more like cosine than this? This looks more like cosine. This looks more like sine. This is number 12. This is number 13, okay? Now, I doubt on a test you're ever going to be asked to match slope fields with their differential equations. But like I said before, working through some of these matching things helps us to at least get our mind around what exactly is going on in the slope field, why it has the shape that it has, and what it's actually trying to communicate to us. I hope that's helpful for the BC kids. The Euler's method videos are going to be coming up next. Those of you in AB can go ahead and skip the Euler's method unless your teacher doesn't want you to. But it's specifically a BC thing for the AP exam. So go ahead and shoot me any questions that are left over after these 3 videos on slope fields, and I'll look forward to hearing from you. Bye.